Sorry about that. So we're going to talk about neural networks today. And I'll start with a quick neural net primer. So if you already have past experience with neural networks, you can try to still learn something more. If not, you can let me know if I need to slow down or explain something better. Right? Before we jump into the talk, I also wanted to mention that if you want, you can follow along. We have a notebook up on a repo. So if you go to github.com/pythonworkshop/TensorBoard demos, if you want to install it on your own machine, you can follow the instructions. They're on the README there. If you're pressed on time or have trouble installing, or for just this session, I've also set up a binder which should let you run it in the cloud. You might not be able to run TensorBoard, but you will be able to run TensorFlow. Sorry. Yeah, sure. So I'll leave it up for a second. And just to get a sense of, all of your past experience, how many of you know how a neural network works? Awesome. How many of you have actually used a neural network to model information? Cool. So I won't probably spend as much time, but I'll still go through the slides just to do a build-up. Okay. Anybody else need this screen on for a second? You're cool? All right. By the way, these slides, I was able to generate them from the same iPython notebook. That's up there. All right. So a brief introduction to neural networks. I'm going to take one step back and first talk about a linear model. So a linear model relates a bunch of inputs, which are x's here, to an output, which is y, such that each change in x linearly affects y. And how do we do this is we come up with a bunch of weights w and a bias term b. And one way to express that linear model is like this, as an equation, all right? And here, in this case, learning or machine learning is the job of, given enough examples of x's and y's, find out the w's and b's that best capture that relationship, all right? I'm going to write this in a slightly different form now. It's in a simple vector notation. Even if you haven't come across this notation before, trust me that it expresses the exact same relationship as the equation above. All right? I'm going to show you the same thing in a slightly different notation, which might be a little bit more friendly, which is a graphical notation. It's the same information being expressed, a bunch of inputs, x's, being multiplied by weights, w's, and there is a single bias term. They're added, giving an output. Clear so far? Okay. Now, what a neural network or an artificial neuron does, by the way, this is a single linear expression, right? So the way a neuron differs from this is that we simply add a nonlinear activation function in front of the summation. That's pretty much it for the typical artificial neuron that's used in neural networks. Can anyone tell me why do we add a nonlinear activation function? Any ideas? No? Sorry? For randomness, you're saying? Yeah, well, it's more for, I would say, giving the model the power to express nonlinear relationships. So if you only have a linear model, then you can only capture linear relationships. Okay? If you have a nonlinear component to it, then by adjusting the weights and biases, now you can start capturing nonlinear relationships or complex relationships in data. Right? Now, I'm going to switch back to our vector notation. So for a single neuron model, All we've done is added this f function on top of the vector multiplication and addition of the bias. Okay, we haven't really done a whole lot. Now, this is for a single neuron. What if we had multiple neurons? Right? What would this equation look like? Well, we would simply add a bunch more columns for these weights. So we'll have one set of weights for each neuron, a single bias for each neuron. So instead of a single B, we now have B0, B1, B through Bm. And correspondingly, we get M outputs back, Y0 through Ym. I'm going to switch back once. This was for a single neuron. This is for M neurons. Okay? And we like to call this a layer of neurons. It has nothing to do with it being an actual layer. It's just one whole set or a sequence of neurons that are being computed or expressed at once. All right? Now, so far, we were dealing with a single input example being passed in. So all those x's were features of a single example that were being passed in. Now I'm expressing basically what happens if we have a bunch of these examples being processed together. Now this is beginning to get pretty complex, but I'm not going to go too far. Okay? I just want to leave you with this view and ask you a question. What do all these chunks look like? Or what are these chunks? Matrices. Great. That's a great answer. And that's what exactly they are. And a more general way of saying vectors or matrices is to call them tensors. And that's why TensorFlow has become so popular in machine learning, is because they represent their unit of data in terms of tensors. And TensorFlow is actually nothing but a way of expressing the relationships between these tensors. And in its library, it has algorithms that can then operate on the relationships you have expressed. For instance, you can present it some input data, for instance, x's, and it will compute y's for you. So it will predict what the features or what the classification label or the regression values should be. You can also give it a bunch of x's and y's, which are examples, and it will then back calculate the weights and biases for you. But all you have to do is express your model in a form like this. Okay? So this was still a single layer of neurons. A deep neural network, in a very simplistic sense, is just a sequence of these layers that are stacked together. So you present a bunch of inputs at the beginning, and then you make them pass through a bunch of these layers, and you get a final output. Now, for a long time, these deep neural networks were hard to train because the training algorithms that came up had trouble dealing with information being passed through multiple layers. I can talk to you in more detail later. I'm not going to go into too much detail here. But recently, due to several advances, both in terms of technology, like we have better compute power now, so we can actually compute these in reasonable amounts of time, but also other techniques have evolved which let us mitigate those problems that were there before. That's why deep neural networks are making such a big impact on pretty much everything. And Google recently put out this library called TensorFlow. They made it open source, so you can go ahead and use it for your own applications. And they themselves internally are using TensorFlow for a lot of their machine learning applications, such as speech recognition and image recognition. So it's a very important and highly dynamic field right now. Okay. So this was all that I wanted to say about neural networks here. Anything, any questions on this before we move on? No? Okay, great. So this was the idea of how to, like, what the structure of a neural net looks like. We'll dive into a few coding examples, going through what do you do with a neural network like this, how do you train it, and how do you test it, all right? So in order to train or do anything with a model like this, you need some data. And for this example, we're going to just generate some fake data, just to be in control of things. But the data set could have come from some realistic problem as well, right? I'm not going to go into much of the code, but basically the set of features, I have 2 columns, so I have 2 features, and 1,000 examples, 1,000 samples of those. I'm only showing the first 10 here, okay? So this is what X looks like. Similarly, I have Y, which is the labels I want to predict. So by the way, I should mention that I'm limiting the discussion to a binary classification task. So for each of those rows over there, I want to predict whether it should be a 1 or 0. And I'm giving it some examples, right? So I have 1,000 of these. Let me visualize it for you. So I've put a little bit of a curve. So these blue dots and red dots are not just linearly separated to give the neural network a little bit of challenge, not too much. And then for training and testing, I'm going to take those 1,000 samples and I'm going to break them up into 700 samples for training and 300 for testing. What this means is I'm going to use the 700 and show it both X's and Y's. And then once the model is trained, I'm going to show it only the X's for the 300 test samples and compare its output with my known ground truth outputs. Okay? So quick visualization of that. It's the same set of points, might look a little less dense because there are only 700, not 1,000 of them. And this is what the test set looks like. So I've just randomly picked samples to be in training and test. Right? This is a pretty standard procedure in machine learning. All right, so I mentioned briefly before that TensorFlow basically consists of defining a model. And under the hood, it's a computation graph. So you're basically specifying the different operations that you want the system to do and how they're connected to each other, what the inputs should be and what the outputs should be. So let's look at how we define a computation graph in TensorFlow, right? We start a TensorFlow session. It's not being used right now, but we'll see how it comes into play. The first 2 things we define are the placeholders for input and output. Now, why do we need placeholders? Is because we can't always push in the entire data set at once. Sometimes you might have a lot of samples, and it might just not be possible for TensorFlow to handle all that at once. So we're going to set up placeholders and then pass in inputs in batches. Okay? So that's what these 2 are for. The X placeholder is basically the set of inputs. And you can see from the shape, I've specified the number of features which will basically be the number of columns, but I haven't specified the number of rows. And TensorFlow is smart enough to accommodate this. So later on, when I give it a batch, it'll put it in the right, it'll extract the correct shape for it then, right? Same thing for Y. Note that it's only a single column, all right? And a quick note on the names that I'm specifying. If I didn't give it a specific name here, TensorFlow always assigns a default name to everything, every computational node that you create, okay? We'll see how that comes into play when we try to visualize the network. So just know that specifying a meaningful name can be really helpful later on in analyzing your network, right? The next one, the next step is basically to create these layers that I talked about before. So first I'm going to define a quick function because I might need this a few times, right? So the way it defines the linear layer is I create a variable here, and in TensorFlow, all these variables are tensors. So weights is a tensor, okay? And I give it a certain initial values. So this is truncated normal, so it randomly picks from a normal distribution. I give it a size of num inputs to num units, so the number of outputs I need from that layer. And then I also define a bias term in a similar way. Details don't matter a whole lot here about how I'm defining them. We can, talk about that offline. What's important is to look at the very last line. That's where the sort of the power of TensorFlow comes in. It's super easy to express an operation. In this case, inside we have a tf.matmul, which is matrix multiply. So matrix multiply the input tensor with the weights, and then tf.add biases. So it's the same operation that I expressed before in vector notation, and then graphically is the same thing being expressed now in TensorFlow's syntax. Is that last line clear to everyone? So multiply the input tensor with weights, add biases, and I'm giving a name to each of these steps. Again, we'll see later on that these names then will show up in the graph that it plots. Okay? Go ahead. Yeah. The weights are there to give the model the ability to set an offset, basically. So if you didn't have weights, then if you think about a linear relationship, then you can only model those relationships that go through the origin. Right? If you think about it like in a simple two-dimensional sense, if you're relating x's and y's, think of the equation of a line y equals mx plus c. If you did not have c, then you can only model lines that go through the origin. Yeah, so in this case, bias is that C term. So if you have a bias term in there, then you can shift the line, essentially, the relationship up and down. And the same thing, the same idea basically extends to multiple features, multiple dimensions as well. Okay? All right. So I'm going to use this function to create a linear layer. Before I jump in, I just want to mention that in this case, we haven't really specified an activation function. So we just did the matrix multiply and added in biases. So right now, we're only able to capture a linear relationship. Okay. Now, when we add an activation function, which is nonlinear, in this case, I'm adding a sigmoid function. Now we're able to capture relationships like this. In this case, what it's doing is it's mapping any value on the x-axis to essentially two levels, two values. In this case, it would be 0 and 1, with a little bit of a quick curve in the middle that jumps up. Now, we could have used a step function, essentially, to model this. But a step function is not differentiable at 0 or at the inflection point. And that makes it hard to learn, because the learning routines that are used compute the gradients or derivatives of these functions, and then try to work backwards from there. So if you have a function that does not allow you to compute derivatives at a certain point, that's problematic for the learning algorithms. Okay, that's why we have this. It's a little bit complicated, but we have this kind of activation function. There is another activation function that has become really popular with deep neural networks. Can anyone guess what that is? Huh? TANH. TANH is a good one, but it's also in the same kind of category as sigmoid functions. Something that is even more popular and even more recent, I guess. ReLU, yeah, there you go. So some people have heard of ReLUs. And these are, when I first came across this function, I was like, no way. I mean, it doesn't really look like it's properly differentiable at that inflection point. How is this working? But it turns out that for computational systems, you can build in some hacks to get around that problem. And in this case, the derivative at that inflection point is basically there's a term called sub-differentiable. So this function is not differentiable at that point, but sub-differentiable, which kind of means that you can pick any slope which is on one side of the line. And there's a whole lot more detail. But for some reason, this activation function has become really popular in deep neural networks. And it's super easy to compute, much easier than the sigmoid function. Okay, that's actually one of the reasons why it's so popular, because it's easy to compute. Okay, so far I've been basically defining these functions, the linear layer, and then the sigmoid layer is basically calling linear layer, but then applying a sigmoid function on top. Similarly, ReLU layer is calling linear layer and applying a ReLU function on top. Now I'm going to use these to actually build the layers. Okay, let's go with a network that has 2 hidden layers, and shouldn't even. I mean, there's nothing hidden about them. It's just that their outputs are not exposed outside the network. And then 1 output layer whose output is exposed outside. So remember, we had a binary classification task, so I only need 1 neuron in the output layer, which will basically say 0 or 1. That's why for the output layer at the very bottom, I've used sigmoid, okay? So that I can easily map to 0 or 1. For the other layers, I've used ReLU. And you can try different activation functions. There are some guidelines you can use to figure out what activation function works best in what domain, or to model what kind of relationships. But in this case, I've basically arbitrarily picked these. Okay. For the hidden layers, I'm using 10 neurons in the first layer and 3 neurons in the second layer. And another thing you might have noticed is I'm saying with tf.namescope hidden 1 and hidden 2 and output. These are kind of optional for TensorFlow. Even if you left them out, you just specify the layer creation, that would work fine. It's just that, again, TensorFlow would assign some default name to each of those operations. And in this case, we just wanted to have a control over how we name things. What namescope does is it gives sort of a higher-level namespace, basically, for the operations that we define within the with block. And we'll see how this looks in TensorBoard. Okay? So that's where I create a simple 3-layer structure, 2 hidden layers and 1 output layer. And then we also need to choose an error metric. In this case, I'm simply choosing L2 or Euclidean distance between the labels and the predicted labels and the true labels. And one small thing to note here is the tf.scalar summary. That's again important because this is how you tell TensorFlow, okay, of all the things, of all the computations that are going on, log this one. So it's not logging everything all the time. You have to explicitly specify which ones you want to log, and this basically says, I want to log this value while it's being computed. So after defining all those operations, you can print out each of those objects, basically. And those objects basically refer to computational nodes in the TensorFlow graph that it's creating. Okay, and you can take a look at this later, but it's just, the important thing is to look at the shapes. So our inputs have 2 columns, 2 features. The first hidden layer will take those 2 features, distribute them to all the 10 neurons, and for each neuron, you'll get 1 output, so you get 10 outputs. And then the second hidden layer will take those 10 and spit out 3. And then the last layer, the output layer, will take those 3 inputs, combine them, and spit out a single number, which would typically be 0 or 1, or one of the values in between if it's at that inflection point. Okay. And then y is the ground truth, and then we're going to compare the output and y, what the difference is, and that's going to be our error metric. Okay. Using this, we can now, small note about how you set up logging. You can look at this later in the notebook. You basically supply a logging directory where you want the logs to appear, and you call tf.train.summaryWriter. Okay, That's how you define the logging object. I'll show you where you actually call it to say, oh, go log. Right, so we can now dive into training. Again, a lot of training algorithms are already built into TensorFlow. In this one, we've chosen gradient descent optimizer. So I mentioned derivatives or gradients. So it computes gradients, and basically it finds the relationship between, changing these weights affects the output in this way or this much. Okay, changing these weights affects the output in this way. So then let me change the weights back so I can tweak the output and make it closer to what the real thing is. That's basically what it tries to do. And so I mentioned changes, right? So those changes are the gradients. Okay, so you say gradient descent optimizer, you bring it back to a point where those differences grow smaller and smaller between the predicted and true labels. All right, so we define the training operation. Again, we give it a name called training. We'll see where that shows up. Now, we've defined the training algorithm. We specify how many times, how many iterations we want to train for, and how many samples we want to send in for training each iteration, right? The first operation is to initialize all the values. We specified how to initialize them before, but this is one, weird or unique thing about TensorFlow. Till this point, we haven't really run any of those operations, even those the initialization operations. We've only defined what the computation should be like. As soon as you call initialize all variables, that even that is not executing anything. It's just defining the initialization operation. When you call session.run, that's when it actually does something. So in this case, it executes the initialization operation according to the parameters we set before. So it assigns random weights from a distribution to the weights and biases. Right. Okay, so this is what the training process looks like. Can be a little involved, but not too complicated. So we iterate for the number of steps we chose. We sample a batch of inputs, just random dot choice from the length of training examples we have. We pick the corresponding features in X train and corresponding labels in Y train and pass them on to the placeholder. Okay, this is a weird syntax they've come up with. You basically use the X placeholder and Y placeholder objects as the dictionary keys, and that's how it knows what values to map to what placeholder. It's an interesting way of solving this issue. And then where it actually does the step of learning is where we call session.run training, error. In this case, we could have just run training because that's all we want to do in this step. We want to run one step of training. But we also want to find the error so that we can log it or print it. So I've just specified that separately. It doesn't run the error term twice. What it does is in that computation graph, it will figure out the correct order of things it needs to do. So for instance, it'll do the matrix multiplications and additions and come up with the output, and then it'll compute the error. Oh, the user has asked for error, let me report it back, and then it does the training step. Okay. Every 100 steps, we print out what the current training error is, and here we also tell the summary writer, okay, log this step. Right. So we can see that at the very beginning, the error is kind of high, and then actually in the very first 100 steps, it falls down considerably, and then it's just trying to optimize. Sometimes it goes a little higher than before. Okay, so that's the training. And then we test our model. So remember those 300 samples that we kept out. We can try and plot them and see what the predictions are from the model. And in this case, we see that there are 7 mismatches. I've circled those, and you can see they're kind of on the boundary between the two groups, which makes sense. And it hasn't been able to fully capture the relationship between these two groups. So some of them it gets, it makes a mistake on, right? So that's what the overall sort of training and testing pipeline looks like. Okay. Now, remember, we've been logging things using that summary writer thing. So how do we view this? Well, we can run TensorBoard and point it to the log directory we specified. It'll pull out all those logs and give you a nice web-based visualization. So let's see if we can look at that. All right. Cool. So remember all the names we gave? This is where they show up. So if I did not give it a name here, hidden one, it would have picked something on its own. Or I guess for name scopes, it doesn't pick anything, and then it would have specified the individual operations along this path. This gives it a nice grouping. Okay. So at the very bottom are the inputs, x. And if you zoom in, you'll see the sizes that we specified. So you can have any number of samples. That's the question mark, but 2 features per sample. Those go into the first hidden layer. This might be from an older run, so I think I had 20 outputs or 20 neurons in the first hidden layer and 10 in the second hidden layer. Let me see if... I don't know. So it actually logs 2 different subdirectories underneath, so you can pick which log you want to run. That goes into the output layer. The output layer predicts a single number, and then I compare that with the known values, and I get an error. And we see that all of these point to training. So the training operation is not directly mentioned in the graph, but what it basically does is it looks at all these values and then tweaks the weights and biases in the hidden layers and output layer, right? So let's dive deeper inside one of these hidden layers. You can click that plus sign and it opens it up. Now you can see we defined weights. These are all names that we specified. This is where they show up in the TensorBoard graph. It takes the weights and the inputs and it multiplies them. Remember, we named it multiply. This is where that comes in. And then we add in the biases. And then we pass it through a ReLU function. And that's how we get the output. Right? So TensorBoard makes it really easy to understand what's going on, especially if you've named things correctly. Okay. Also mentioned in this layer are how the weights are initialized. They're initialized using the truncated normal function. And then also where else these weights and biases are connected. So in this case, the training operation actually affects these weights and biases. That's why it's mentioned here. All right. So hidden 2 is pretty similar, so I'm not going to open that. Let's open output. Pretty similar stuff, multiply, add, but instead of ReLU, we have sigmoid, like we mentioned. And what it does is it, till this point, we had whatever number of neurons there were in the previous layer, that many columns coming in. The multiplication reduces it to a single number, and then we add a single bias value. The sigmoid simply transforms that into 0 or 1, and that's what we see as output. Last thing I'm going to show you is the error term. Okay, it's a very simple one. So this is a default name that TensorFlow has picked. So let me switch back to code so you can know where this is. This operation here, logits minus labels, that's what TensorFlow has given a default name of sub to it for subtraction, I'm guessing. All right. So you subtract those, you compute the L2 norm of that value, and you see this small icon here. It means these values are being logged somewhere, right? So this is the general sort of shape of the computation graph. Let's look at the logged values. And you can plot multiple runs to compare them as well. This is what that L2 loss looks like. So remember, we had a high loss at first, and then it started dropping off. It went up and down a few times. So you can really diagnose how your neural network is performing by logging this loss. And if you want to really solve a problem that you're having, these kinds of sort of visualizations can be really important. Okay. So that's pretty much all I had. There's another thing I didn't explain here. Another way to log values is to store a histogram. So for instance, for weights and biases, it would be hard if you were logging the individual values. So instead of individual values, you could log a histogram of values. And it usually typically shows you how the distribution of weights and biases change. So that's another thing you could do in TensorFlow. Yeah, that's pretty much it. If you want, you can go to that repo and check out the code. It's the same notebook that is, it's fully functional, so you can step through it. You can export it as slides using NB-convert, I think. And then, that's what this presentation is. Yeah, that's all I had. Time for a few questions, maybe? Yeah.
Is there a place to adjust the learning rate and gradient descent function?
Yeah, absolutely. Yeah, that's a great question. So the question was, is there a place to adjust the learning rate in the gradient descent function? In TensorBoard?
Yeah.
The problem is TensorBoard is only for visualizing the output. So you can't really tweak anything there that will affect the computation, okay? But for instance, here, when picking our training method, we specified the learning rate that's passed in. Yeah, go ahead. Sorry, can you actually come to the mic? I remembered.
I got two questions. One is, it seems like, a lot of stuff kind of like still like the old neural network to me. So why it is called a deep learning? How to differentiate like a deep learning from like a normal like learning?
Right.
Another thing is for the TensorFlow itself. I mean, what's the advantage of using TensorFlow instead of using, let's say, some like a relatively decent sample size, even in a MATLAB, because it's either in matrix manipulation, or use like a Google's like a Torch. I mean, Lua, they use that internally for DeepMind or whatever, and other competitor like this afternoon someone talked about the Cafe, and even the Microsoft recently has like a really some benchmark to say 10 times, can beat the TensorFlow.
Yeah,
Thanks.
that's a good. Those are two really good questions. So first, I think is, what's special about deep neural networks and how they're different from more shallower networks that we've seen before. Like I mentioned, like over the past, I guess, a couple of decades, we've seen a lot of improvement in just computational technology, which makes it possible for us to now actually train these networks. Like earlier, we had people who were coming up with these designs for really deep networks. It was just not feasible to train them. Like you had to run them through a lot of different training examples in order to get any reasonable output. Also, in addition to that, there is a specific problem called the vanishing gradients or exploding gradients problem, which basically the issue is that when you observe a small change in the final output layer, and you try to trace back its influence, like how it's being influenced by the different weights along all these layers, at the beginning of the network, that influence reduces to a very small amount. And so just using that as the signal to tweak the weights and biases wasn't really giving us anything useful. So you weren't really coming up with a good way to tune those weights and biases. But now we've come up with different techniques, including using the ReLU activation, which slightly mitigates that problem, and also other techniques like regularization, which have made training possible. So they're no different from neural networks that were there before. It's just that they've become more feasible and more practical to train. Okay? And your second question was about why TensorFlow and not some of these other libraries. You know, you can use any of these libraries like Caffe, Theano, TensorFlow, or I think Microsoft's CNTK. I think, you know, each of these libraries approach this problem of defining the network from a slightly different point of view. Like I think in Caffe, you don't write code to define the network. You define it in a data format that they have. So it's really easy to get started defining neural networks in Caffe. But after a certain point, you reach, you know, I might want to tweak this operation a little bit. I might want to change this operation a little bit. That's where it becomes a little harder. With TensorFlow, each of these is basically an operation that you're defining in code. So you can come up with, you know, it's slightly more customizable. It still takes a little bit of effort, but so you have, you know, all these different libraries. They're essentially trying to solve the same core problem. They're essentially doing matrix multiplications. So you could use MATLAB as well. Different libraries have different, you know, pros and cons. One of the great things about TensorFlow is TensorBoard, I think, because it lets you visualize the network that you create so easily. Yeah. How do we store our models? Okay. So there are two things that you need to store a model. One is the structure of the model, and then the second is the weights and biases, right? The actual values that you put in. So there is a way to store TensorFlow models I didn't explain here, but you basically can write it to disk, and it has its own internal format. It stores the structure there, okay? In addition to the structure, if you've trained the weights and biases, it will store the values as well. Okay, so you know, again, different libraries will have their own formats, but you can serialize this basically. One way to store it would be to basically store it as code, right? The code that you use to define the model, that's your structure, but you also need to store the values, which are basically giant arrays or tensors. So it has a format for that. In fact, the next talk coming up is going to talk about how you can take a model like that and then put it up for some other application like prediction over the web. Yeah, cool. Yeah.
I have a more general question. How do you decide how many layers and how many neurons to put in each?
That's a really good question. How do you decide how many layers and how many neurons to put in each layer? So think of the more neurons you put, the more expressive a model can be. Okay, so when you're trying to say capture a very simple relationship, like there's just these two classes of data and there's, you know, a simple distribution, then a fewer neurons, a small number of neurons are probably enough. But when you're trying to capture a more complex relationship, for instance, when you're doing handwriting recognition, okay, say there is this shape 7, okay, what the neural network has to do internally is to reason, saying that, oh, if there is a flat line on the top and there is a curved line on the side, then it's a 7. If, you know, we have a curve here and a curve here, then it's a 3. And so it's trying to model very complex relationships. When you have that need for a more complex relationship, that's where you need more neurons, okay? You also need more layers depending on, you know, certain aspects of the data you're trying to model. Now, it's not really a perfect science coming up with the number of neurons and you know, how many layers you need, but it depends on I guess the, you know, nature of the data and how complex it is. So sometimes you need more layers when you have these complex decisions that the model will eventually need to take. The width of each layer sometimes depends on the number of classes you're trying to predict, the number of different patterns you expect to find in the input data. And yeah, I mean, various other factors. But most of the time, you'll see someone coming up with one example and then slowly tweaking it. Okay, let me try 10 more neurons, or let me try 2 more layers, and coming up with it. So it takes a lot of trial and error, I would say. Yeah. So let me understand your question correctly. So it's about regularization and how you would introduce regularization into the fold. I mean, TensorFlow actually has good support for regularization. So you basically say, in the training method, basically you say that, okay, use this learning rate and use this weight for the regularizer term. And it internally computes like, okay, for each learning step, I'm not only going to compute the error based on, not the error, but I'm not going to compute the updates just based on the differences that I'm finding. I'm also going to constrain them using this term. And that's what regularization is. So yeah, it's actually not hard to implement that in TensorFlow. And I can talk to you offline about it as well. Cool. How are we doing on time? I guess we're pretty much over. So any other general questions? Otherwise, yeah, go ahead.
I've heard TensorFlow is really good at kind of working in parallel systems. How does that get set up in this system? Do you have to set up different models on different systems and just pass the tensors between? Or is it naturally?
That's a good point. I think that's one criticism of TensorFlow. I've heard that it's hard to, like, it makes you do more work to make it work on distributed systems. But basically what you do is when you're defining these different operations, you can specify, oh, do this operation on this device, do this operation on CPU, do this operation on GPU. And in TensorBoard, when you look at the graph, it lets you sort of filter by device. So in this case, all these operations are running on the same device. That's why they're all the same color. But if I had them running on different devices, it would show them here. So you can do that. And then I'm not fully familiar with how Google does its full distributed TensorFlow, but there is a way to specify how to run things on different machines in a cluster as well. But I mean, once you define, what operation to run on what device or machine, then TensorFlow internally figures out how to route that data. Cool. I think we're pretty much over on time, so we can wrap this up, right? Or 9 minutes? Okay. So yeah, then. Right. Okay, so the question is about whether we can spread out a single computation over multiple machines or multiple devices. I'm not fully sure about that myself, but I think, internally when it has a giant sort of operation to do and it's not possible for it to do in one step, then TensorFlow will internally decompose that problem. But I don't know if it can spread it to different machines. I know there are other libraries which sometimes can do that, and you can specify what resources to use, but I'm not fully sure about TensorFlow. Sure. Yeah.
There are a couple of TensorFlow abstraction libraries. Do you recommend those?
Yeah, so TensorFlow abstraction libraries, basically TensorFlow in this raw form can be a little intimidating to use. Sometimes, we've come we become accustomed to the more scikit-learn form of machine learning, where you define a processor and it's kind of black box, and you pass in some values to the fit function, and then you call the predict function to predict. And if you are already in that kind of mindset, then yes, there are some wrappers or abstraction layers which will help you use TensorFlow in an identical way. So I think it's called skFlow, and it's become part of the overall contributed packages in TensorFlow now. So you can use that. I think it does limit you in a few ways, and like how you can structure your network. But again, for the most part, I think you will probably be able to get away with an abstraction like that. I think either skFlow or tflearn, those are the two that I've come across, and it depends on what sort of syntax speaks to you the most. So internally, they're still using TensorFlow, so it's not too different in the way they operate. And yeah, I mean, you can try one out. I don't think either one of them has become stable enough to become a single sort of recommended choice yet. It'll depend on, I guess, the TensorFlow devs also adopting one of them. So we'll see how it goes. Any other questions? Let me keep the initial slide up. So you can go to that repo. Install it. Instructions are in the README as well, the same thing. And yeah, I mean, try out. I would actually love to see if you play with the neural network, change it, add some layers, change the sizes of those layers. You can even take just a completely different TensorFlow model and tweak that, or come up with one on your own. If you play with it and generate a graph, a TensorBoard graph from it, tweet it out, and I'd love to see what you all come up with. And I'll be around all day, so if you have any questions or get stuck with anything, let me know. And yeah, have fun.